Right, so let's have a look at this tutorial. What we're going to try and do is we're going to try and plot our pulses. And then we're actually going to superimpose the pulse with a few frequencies added to see what it looks like, and also to look at the frequency response of the pulse. Okay, so in this case we have 2 pulses per second, so our frequency is 2 Hertz. So we should say our fundamental frequency at 2 Hertz, 4, and then a harmonic at 4, 6, 8, 10, and so on. Okay, so what we'll do is that we'll just get started here. So what we'll do is we'll just copy the Python code and then have a look at the code behind it. Okay, so we'll just grab this code here. Hopefully it should copy it, okay. Let me just paste this in. So I'll paste it in and then we'll run it and then we'll go back and have a look at it. Okay, so we'll just run that. Okay, so there's a frequency response. Okay, so the Python program does 2 things. One, it gives us the amplitudes as a value. So we can see for 0 Hertz, that's our average value. We get 1, which is to be expected. Okay, because it's 5 times the 0.2 gives us 1, and then we go up to 1.87, and then go down, and then you see at 10 we're down at 0 almost. That's 0, and we've plotted the output pulse waveform if we just use some of the first few frequencies. Okay, so we'll have a little look at the code and see how it works. So our file is Python tutorial 10. Okay, we can take a few arguments in here if we want. What we can do is we can put in a file name for our outputs. We can put in a duty cycle and a frequency, and it should plot for us. But as a default, we're going for a frequency of 2. But if we want, we can actually specify that. So the duty comes second and then the frequency. So we can run it with the file that we want to put out. We'll do 0.5 and we'll do 5 Hertz. Oops. Just run the code. Okay, so we can see we're on 5 Hertz now, and there is a duty cycle of 0.5, which is really just a square wave. Okay, so you can either use the arguments to pass some values in, or you can just hardwire them into the code. Okay, so that's what this part is doing here. It's taking the arguments, detecting how many arguments that we have. Okay, and for this we're creating our sine wave. We're creating a square wave here with a certain duty cycle, and we're just making sure that it sits between 0 and 2.5. After that, we take the Fourier transform of it, and then we're going to plot the absolute value of the Fourier transform. I'm going to output the values for the amplitudes for each of the frequencies. And then what we do is that we take, in this case, we take cosines, and then we add in the amplitude that we've determined from each of the harmonics, and we rebuild the waveform from there. Okay, so after that we plot it with a green line and it's dashed. That's the option that we add for adding that plot. And we can save it as a SVG and also as a PNG file, and then we just show it to the screen. Okay, so that's our code there. That's how it runs. Okay, so what to do next is to try with different frequencies, and then with different duty cycles to see what you actually get. Okay, so in this part here, we're going to look at different duty cycles, and then we're going to confirm what the actual average value is. After that, we'll add in other frequencies to be able to show that our waveform becomes closer and closer to the end result of our square wave. Okay, so we would go in and we just copy that one, and then we would add in there. We put a slash in there, if I can find where that is on my keyboard. That's it there. Okay, so that adds in another one there. So let's just check, that's fine. Okay, we'll just save that one. Now we'll run it again. And hopefully we should start to see our waveform moving more towards a square wave. We've seen already that it's starting to look very much like a pulse. Because we've used cosines, there's a slight phase shift there, but this will become flatter here, and we should get a flatter top to our pulse. Eventually, if we used lots of frequencies, then we'd almost get our square wave back, because you see the values are reducing as we go up, and hopefully have a lesser significance. But this is really what happens if we apply our pulses to a limited channel, limited frequency channel. In this case, it might be limited up to 16 Hertz. Then we can see what the pulse waveforms would actually look like. Okay, so go ahead and have a look at this part of it too. Okay. So that's been an introduction in how we can resurrect our waveforms.